Section 26.5, the dispersion of light, prisms and rainbows. So the question I want you to be thinking about with this section is, why do we see rainbows? So to answer that, we'll need to take a look first at prisms. So the prism is just a triangular piece of glass, right? Usually a chunk like shown here. And the net effect of a prism is to change the direction of a light ray. So if we send in a light ray like this red light of a laser, it bends when it encounters the interface with the glass, and then it can bend downwards. The light that's coming in can then suddenly be going down instead of upward. So the direction is changed. Interestingly though, light rays corresponding to different colors bend by different amounts. So if we send in some white incident light, then the red doesn't bend quite as much as the violet bends a lot more. So we get this separation and we start to see a rainbow effect just within the prism where the light is spreading out. Now, why is this? Well, it has to do with the indices of refraction at changes depending on the wavelength of the light. So red has an index of refraction in crown glass of 1.52, but violet is all the way up to 1.538. It's a larger index of refraction. So it has a larger N value. It's going to have a larger overall a larger amount of bending compared to the red. So that's a really interesting difference to see. And prisms pop up a fair amount, and they can have some interesting effects. So here's a conceptual example. The refraction of light depends on two refractive indices. So it's possible for a prism to bend light upward, downward, or not at all. How can the situations depicted in the figure arise? So we just saw some examples where the prism is able to bend the light downward. Again, still following Snell's law, the law of refraction. But here, in the yellow one, case A, the light starts going in and it bends to a larger angle as it's leaving the prism instead of bending downward. In case B, it doesn't bend at all, so it's not going to a larger angle or a smaller angle. How can that be? It's the same glass prism in all the cases. Well, what has changed, when we get some clues here based on the coloring, is what the prism is in. So typically, like in the examples shown before, the prism is just in air, which air has a refractive index of 1 compared to crown glass that on average has an index of refraction of 1.523, that air and the surrounding gases are going to be a lower refractive index, and so that will bend the light downward. But if we instead place our prism in a material with a higher refractive index, like maybe we place it in some carbon disulfide that has a pretty high refractive index, that's now a greater refractive index than the crown glass, right? Carbon disulfide is 1.632, the crown glass is 1.523. So that can cause it to bend upward in this case. It's even possible that we place our crown glass in a material that has the exact same refractive index. In that case, the light passes right through and it looks as though it is invisible, like the prism has disappeared. It has no effect. So that's really fun and cool to see. You can find videos that show that as well. And these ideas now give us the basis for understanding rainbows. So rainbows are formed by water drops in the sky along with the sunshine. It's key to have both the sunlight and the raindrops. Why is that? Well, the sunlight passes into the water droplets, like the clouds or the raindrops in the sky, and the light then refracts and separates by different amounts. The red versus the violet are the two extreme examples, with all the colors in between those two. Then on the back of the water droplet, it reflects, right? This is our total internal reflection, and the light comes back out. And so then there's red that comes out at one angle and violet at another angle. Well, depending on where the droplets are, they all follow the same pattern. but there's a certain height of drop that's at just the right height for the red to reach our eye, and the violet will pass right on by. So we don't see that drop, just looks red to us. Similarly, there's another drop that's lower where the red misses us, but the violet is now able to make it to our eye. And so what we see in effect when we look at these drops is we see red on top going down, orange, yellow, green, blue, and violet on the bottom. We see the full rainbow effect, which is amazing. And it just has to do with the angle that we are relative to the water droplet that's being illuminated by the sun. So if you've ever been fortunate enough to see a rainbow from the sky, you'll see it's actually a circle. There is no pot of gold at the end, or maybe there is right at this intersection point. I'd be pretty curious to check that out. But you'll notice if you go there, the rainbow has moved, because the rainbow is just how the sunlight is illuminating the drops and making it to your eye. You also, this one's a little easier to see more often. On a really bright rainbow, you're able to see another rainbow around it. Double rainbow. What does it mean? It's so beautiful. Well, the double rainbow, again, comes from physics. For the double rainbow to work, instead of just having the single reflection off the back of the drop as before, it actually has a double reflection. So the light comes in, reflects off one side of the drop, reflects off the other, and then comes down to your eye. And so the secondary rainbow is at that larger angle, and it loses a lot of the intensity in the process. That's why it's harder to see the secondary rainbow. Another interesting effect is because of that second reflection, the double rainbow, the second rainbow, is actually flipped. It's a mirror image of the other. So if our first primary rainbow is purple on the inside out to red, the closest to the next red is another red spot, and then it goes out to purple. So it's inverted from that. So that's pretty cool. Double rainbows can be explained as well. And so, yeah, now you know the answer to why rainbows look the way they do. And you can go find a rainbow. Something that always helps is, in order to see a rainbow, you'll need to be able to see your shadow, as well as see the raindrops that are being illuminated by the sun. So late in the day, if it's raining nearby, that's a great rainbow weather to check it out. One more note, an application of prisms is they're used by NASA all the time. One example is the Landsat, which is a spacecraft that is more than just a camera with a great zoom lens orbiting Earth. It measures light reflected by Earth from the sun. So the light that Landsat measures tells us a lot about Earth's surface, since different surfaces reflect various types of light. So you can learn all about all of Earth's surface just in looking at the reflection. And so the scanner breaks up the image into elements and records some of that. And so this sweep of the scanner's mirror prism, antenna, or other element across the track, straight, circular, and other shapes. So prisms are used within this spacecraft in order to get these observations, right? It also mentions a device that consists of a rotating disc that exposed a neutral density filter, which is a prism, which projected light from calibrated tungsten lamp assemblies during each return oscillation. That's a lot of fancy words. I don't understand all of it, except for to say that they're using prisms even on spacecraft here. And one of the interesting uses of this spacecraft is the way it can observe how the land is changing. So here's a photo of a lake that's taken 20 to 30 years ago. And you can see back in 2017, the lake is now smaller, right? It's lost some of the edges of that. And that was observed with this Landsat 8. Pretty remarkable, yet another application of physics in action. Okay, we will wrap up there.